Okay, this is Unit 7, Video 1 on centripetal force and centripetal acceleration. Okay, so we are moving into a unit on rotational motion, things going in circles, okay, around curves, things like that. Today we're going to talk about center-seeking forces. It's called the centripetal force, and we're going to learn how to solve some word problems using the centripetal force. Okay, first few things that you need to know, or at least think about here. So you already know that when a car speeds up or slows down, that there's an acceleration. Right now we've been calling it the linear acceleration, right? Anytime it speeds up or slows down. Think about what you feel when a car drives in circles at a constant speed. Is that car accelerating? The answer is yes, okay? Even though it's at a constant speed, because the car is driving in circles and because velocity is a vector, do you remember, hopefully, that A is a change in velocity, so v final minus v initial over time, right? So acceleration, the definition, is the change in velocity over time. So the number doesn't have to change if the direction changes, and I can kind of prove that to you here. So if the car is still going at 5 meters per second, but one time it's going at -5, going to the left, and one time it's going to the right, then we would have the final being +5, initial being -5, let's say it takes 2 seconds, okay, and we'll have 5 minus -5, which becomes positive, and you end up with A equals 5 meters per second squared. That was just a lucky thing that it came out to 5. But either way, this car is accelerating even though it's going the same speed, but it changed direction. It went from +5 to -5, or the opposite, okay? So anytime anything's going in a circle, it's constantly changing direction, and so we say that it is accelerating, all right? Now the centripetal force, or the center-seeking force, this is a force that's going toward the center of the circle, okay? This force and the accompanying acceleration keep the object turning in circles. This force always pulls toward the center. The centripetal force is always some other force. So the centripetal force is not a force on its own. It's not a new force. It's just all the other forces we've learned about, tension, friction, normal force, gravity, pulling toward the circle, okay? It's not a force on its own. So it's built from other forces. The equation, I'm going to give you two equations. I'm going to give the equation for centripetal acceleration. Okay, we'll put a little c so you know it's centripetal, meaning toward the center of the circle, is v squared over r, okay, the radius of the circle. I'm going to also give you the equation for centripetal force, okay? If force is ma, then you know that force is m times a centripetal, which is v squared over r. Okay, so this really just says ma centripetal, all right? Units for a are always meters per second squared. Units for force are newtons. Okay. Now, just so you kind of have a picture of this, car goes around in a circle. The centripetal force is pulling toward the center. Okay. So no matter where it is on the circle, it's pulling toward the center. Okay. And that's what keeps it going, right? It would want to go this way, right? Inertia would want it to continue going straight, but this force pulling this way keeps it going sort of in this direction, right, at this moment. And then later on, same thing, it wants to continue straight, but this force keeps it going sort of in this direction. And so that's what keeps it going in a circle, okay? Couple of things here at the bottom. To find the maximum speed that a car can take, this is what we would use this concept for, okay? So if we wanted to find the maximum speed that a car could take a corner on a flat road without skidding out, we would set the force of friction equal to the centripetal force, okay? To find the tension in a rope of a swinging pendulum, remember that it's the sum of the tension and gravity that produces a net upward force. We're going to go over all this. This is just some stuff for you to see here. A common mistake is just setting the centripetal force equal to tension and forgetting gravity. I'm going to show you what I'm talking about. And then to find the speed of a planet or satellite in orbit, set the force of gravity equal to the centripetal force. Okay, so these are just some applications of where we can use this stuff. Finding the speed of a planet is important. Finding how fast cars can go around corners without skidding out is important. That's how we get speed limits and things like that. Okay, so these are practical applications. All right, turn the page. Let's do some examples because this is where it gets kind of strange. So example problems, remember the centripetal force is not a new force. Not a new force, okay? It's just a way to describe how our old forces, tension, friction, normal force, cause changes in direction. It may help to continue asking yourself what force is causing the change in direction, all right? Now we're going to do an example with where friction is the centripetal force, normal force, and tension, okay? So you can kind of see all three. All right, so let's just start. So a 1,100 kilogram car, so I'm just going to put down my variables here as I go. Turns in a circle with a 25-meter radius. R is radius. Tires of the car have a coefficient of friction. That's the mu, not a force of friction, a coefficient of friction. 0.7. What force causes the change in direction? Okay. What is the maximum speed the car could travel to not skid out? So we want V. Now, if we look at a picture of this, right, this car is going this way, right, and it's going in a circle, like around a curve, okay? Now, the car wants to continue out. It wants to continue straight, right, in all directions, no matter where it is, it wants to continue out. The thing that keeps it going in a circle is the friction between the tires and the ground. Okay, you can imagine if you were trying to drive in a circle on ice, that it would be really hard to drive fast in a circle on ice because there's barely any friction. Okay, and that's why we kind of skid out of the circle when the roads are wet or oily, because we don't have enough friction to keep us in. So the force that's pulling toward the center is friction. Okay, there's nothing pulling out of the center. There's nothing pulling the car that way. Okay. Inertia makes the car want to go this way, but that's not a force, okay? So the only force we have here that's in the direction of the center of the circle is force of friction. So in this case, we're going to set the force of friction to equal our centripetal force. The force of friction is acting as a centripetal force. It's pulling toward the center of a circle, okay? So now we just plug in our equation. So force of friction, we have mu times the normal force. Centripetal force is mv squared over r, okay? Plug in what you know, 0.7. Normal force is mass times gravity, so 1,100 times 9.8. Mass is 1,100. V is what we're looking for. R is 25. Okay. And if you go ahead and plug that in, you end up getting V is equal to 13.1. Oops, not squared, meters per second. That's the maximum speed a car can go around that curve with that mass, okay? All right. Let's try this example. Now this one's a little confusing because of the way it's written, so I'm going to clarify this here. So normal force example. In a roller coaster, the cart and passengers have a mass of 500. If they travel at 20 meters per second around a loop with a 40-degree radius, meters, okay, how much force or weight must the track be able to withstand? So what's not clear is that I'm actually going to pretend they're on top of the loop, okay? So they're going around on top. They're not hanging upside down. Does that make sense there? So they're kind of going around like that, all right, over a loop. We can do if they're hanging underneath, but we're not right now, okay? This is just going to be on top here. So here's the idea, okay? You got to be really careful here. So there is a centripetal force, but the centripetal force is other forces, okay? So what forces are on the roller coaster at the top of the loop, okay? That's where the roller coaster track is going to have to counteract the most gravity, right? At the top, okay? You can imagine that they're underneath over here or something. I don't know. Doesn't matter, okay? You have, you know what? Let's put them on the inside. Sorry, let's do that. That makes more logical sense, and we usually do that anyway. Okay, so if we have the loop, okay, it's like this, all right? The spot where the track is going to have the most normal force, or it's going to have to carry the most weight, would be at the bottom, okay? Because up here, you can imagine gravity's pulling down, so the normal force doesn't have to be very much, right? In fact, it's almost zero. So, and on the sides, right, there's not as much gravity pulling down toward the track as there is here. So here we have the force of gravity pulling down, and we have the normal force pulling in, or up, toward the circle, okay? Now, in this case, do you see that the normal force is pulling toward the circle, and the gravity is pulling away from the center of the circle? The center of the circle is here, okay? So what we have to do is we have to basically set up an equation that says that the centripetal force is equal to the force pulling toward the center of the circle, the Fn, minus anything pulling away from the center of the circle. And that's the thing. Most people will forget to subtract the weight pulling away from the center. So toward the center, away from the center. You can imagine when we do like net force, that toward the circle is positive, right? And away from the circle is negative. That's not really how it works, because if you went around the circle, it would just be different. So you just want to make sure you write toward the center minus away from the center, okay? Centripetal force is mv squared over r. Normal force is what we're actually looking for. We're trying to figure out how much does the track have to push up to keep the car from falling through. And the weight is actually the actual weight of the passengers in the car. So this would be 500 times 9.8. Okay. The minus is already in there because I know that it's going downward. So I already included the negative, so you don't need another negative. All right. So now we can plug in the rest of our numbers here. This is 4,900. Okay. If you do all the math, you plug in, you get normal force is equal to 9,900 newtons. That's how much weight the track needs to be able to hold, okay, at this point in time. Because the gravity is pulling down, okay, and the cart is going so fast that it's actually trying to sort of go out of the circle, right? It's trying to go parallel to the circle. So there's sort of an extra force pushing down on the track. So that's why this is bigger than gravity. All right, but the main idea is that the centripetal force equals forces. I'm going to put this up here. I want you to write this down. Centripetal force equals the forces toward the center minus the forces away from center. Okay. Now, in this example, we didn't have anything going away from the center. The force of friction was pulling toward the center, but there was nothing pulling in the opposite direction. So that's why this just said centripetal equals friction. Okay, we didn't have anything pulling away. All right. Let's do one more example here. All right, so David plans on slaying Goliath with a sling. If the rock has a mass of 5 kilograms, and the rope is 3 meters long. That means the radius is 3 meters long, because you can imagine a rock on string and he's holding it here. He's going to swing it around in a circle, okay? The length of rope is the radius, all right? This is going to swing like that, okay? If the rope can withstand a 400 Newton force, that means the tension in the rope is 400 newtons at its max, okay? Then what is the maximum speed the rock can travel? So how fast can it go around in a circle? So you have to think about this. You have to think about the spot in the circle where the tension is going to be the highest. Okay, because that's kind of our breaking point. If we pick where it's going to be the lowest, that doesn't help us. The maximum force it can withstand is 400. So around the circle, the spot where the maximum tension would take place is at the bottom, because we have gravity pulling down, okay, and we have tension pulling up toward the center. If you think about it, it's just like the roller coaster. At the top, there's not going to be much tension because gravity's pulling down toward the center, right? So tension would be 0. But in this case, this is the most tension we can get, okay, is if we have all of gravity fighting the tension. Okay, so let's set this up. So centripetal force equals forces toward the center, so tension, minus forces away from the center, gravity. Okay, and now we just plug in mv squared over r equals tension minus force of gravity, or mg. So we could put that in there. Okay, we have m, we're looking for v, we have r, tension is 400. This is 5 times 9.8. Okay, and if you do the math and you solve it out in your calculator, whoops, you get V equals 14.5 meters per second. So that's the maximum speed he can swing it without the rope breaking. Okay, and the rope would break at the bottom. Okay, the rope would break at the bottom if it were going to break. All right, because that's where it feels the most tension. All right, last little note, a G-force, sometimes you're going to hear us talk about a G-force like in some of the videos and stuff. A G-force is a multiple of the acceleration of gravity. So like if you experience 1 G, you're basically in free fall, okay, because you're experiencing negative 9.8 meters per second squared of acceleration. If you experience 2 Gs, you're experiencing 2 times that acceleration. So 1 G equals negative 9.8 meters per second squared. Okay, 2 Gs would be like negative 19.6 meters per second squared. So the more Gs you're feeling, the more acceleration you're feeling. Okay, and we sometimes talk about this in like rotational motion, rocket, like astronauts will feel like, you know, up to 15 or whatever Gs when they exit the atmosphere. Okay, so just keep in mind 1 G is equal to an acceleration. It's not an actual force, it's an acceleration. Okay, so that's just a note for when we watch videos and stuff. All right, see you in class.